Welcome back to lectures on machine learning. So what we have done previously was to talk about linear regression models and introducing a very simple model, and what we have seen through a data walkthrough example that you can find a good enough model, and you can judge the efficacy of the model by estimating its parameters and also computing the confidence intervals of its parameters, right? Okay. And if you recall that I have also said yesterday that when you estimate the parameters, there is a closed form expression that you can obtain, right? We did not show the closed form expression because what we want to do today is to derive that closed form expression from the principle of maximum likelihood estimation, okay? And then introduce MLE, go to map, okay? And then talk about some other nuances of regression model. So we'll continue with this regression model, but we would, interpret different nuances of the regression model from the principle of, statistical machine learning. Okay. So just for a quick recap, we know that, so today is MLE, which is maximum a parametric method, as we will discover soon why, okay? And also these are point estimates. We will also talk about these later on. All right. Because you would actually try to localize the parameters of your density function or distribution. So if it's a Gaussian distribution, then your parameters are the mu and the sigma, right? The mean and the variance. You would actually want to know, where should you locate the mu in order to obtain like a greater probability of a particular event happening or a particular class level. Okay. All right. So just recall that we go to this. We have seen this, that regression model is actually nothing but minimizing the errors, and it's actually nothing but a least square minimization of error. Okay. All right. And you actually write it as a constraint. You can write it as a constraint optimization problem by minimizing the squared objective function subject to some constraint, and that constraint is that the average error will have to be 0. Okay. All right. So that thing being out of the way, I will come back to this in just a minute. Okay. So let's recap what we know about linear regression. Okay. So the MLE on linear regression model is something like this. You have labels to predict. Okay. And you have the coefficients, which are the regression coefficients to estimate. These are the regression coefficients to estimate, right? The errors, this is the error that we wish to minimize. Estimating the parameters of the model by estimating the parameters as we can, right? And this guy X is nothing but a data matrix. Yesterday we have seen examples of this data matrix. Remember the CPU output versus processing time versus the number of input output devices, correct? So also I would like to reiterate at this point of time that this vector which contains the parameters also includes the bias term of the linear regression, and the errors are assumed to be normally distributed. Okay. All right. Now what we claimed was this, right? Remember, we claimed this for the linear regression model, and then we kind of extrapolated this to a locally weighted linear regression model where we had just inserted the weight term, the hyperparameter, into the pseudo inverse, right? So this, when you are estimating the parameters, we have an expression which says that this is X transpose X inverse, okay, times X transpose Y. Okay, this X transpose X inverse is known as the pseudo inverse, right? This is required to do because your data matrix is essentially not square, it's in rectangular matrix, and so you multiply it with its transpose to make it square, take the inverse, and blah blah. Okay, all right. So the question is, where does this come from? Okay, we have just seen the expression, we have plugged in the values and we estimated the parameters and we computed the confidence interval of these parameters, right, for the motivating example that we have seen yesterday. But the question is, where does this come from? How do we get this? Okay, all right, okay. So let's look at general least square, which is nothing but I minimize, okay, over all data samples the difference between the model, all right, and I'm just considering one independent variable, okay, with multiple instances of the independent variable, okay, and two parameters, okay, a1 being the bias and a0 is the coefficient of that, okay, all right. And we like to take a look at the square of the error term and minimize the square, and this guy is known as residuals, right? Okay. Now, if we have a vector notation, in vector notation, what this would mean is the following. We write, so this is nothing but the error term, right? This is nothing but the error term. Okay. So if I write the error term in the following manner as an n by 1 column vector, right? And then you have bunch of labels that you get from the data, and then because of the bias term, the first column would be identically 1, right? And then you have the different instances of the input variable, okay. It makes sense. I think this is also n by 1, this is n by 2, and this is 2 by 1, so this also becomes n by 1. So I mean, at least from a dimensional point of view, we are okay, all right. But this can be just in a neat form. I mean, assuming everything is a vector, I can write the error vector as y minus x b, okay, all right, okay. Therefore, when you are the regression problem, in other words, the error minimization problem in a vector notation can be represented in the following manner, that you have since we are considering the square of the error, and this can be, we have seen yesterday that this can be written as the error transpose error, right? So in other words, the error is y minus xb, right? So you can write this as y minus xb transpose y minus xb, okay, all right. So what's the objective? The objective is to minimize this guy, okay, y minus xb transpose y minus xb with respect to the parameters p. So this is my problem in a vector notation, okay. Now we have to do this really carefully. So in other words, what we are trying to do is we are trying to take the partial derivative of this, okay, and use the concepts of basic calculus, set this guy equal to 0 and try to estimate the errors from here, okay. All right. So probably what we should do is, at this point of time, I'll clear out this screen, and I hope you are okay with whatever we have done here, okay. But we have to do this really carefully because it involves a few steps, okay. So let me, before I actually start doing the minimization problem, you have to rewrite this. So I mean, what we are trying to do is this, we are trying to do this, okay, all right. And we will have to expand out, because it's in a vectorial notation, right? We'll have to expand out a few things. So let's do some linear algebra here. So if I do this y minus xb transpose times y minus xb, what I get, you know that A plus B transpose is B transpose plus A transpose, right? Okay, so what you are going to get is minus XB transpose plus Y transpose. I'm just writing the Y in a small notation now. I mean, I hope that's all right. And then you multiply this by Y minus XB. Okay, all right. And then term by term product, you are going to get minus B transpose X transpose Y plus B transpose X transpose X B plus Y transpose Y minus Y transpose XB. Okay, all right. Now this can be written in the following fashion. This can be simplified and can be written in the following manner. So I can write this as Y transpose Y minus 2 times B transpose X transpose Y plus B transpose X transpose XB. Okay, all right. Now, I mean, it needs to be seen that, I mean, if you look at the X transpose Y thing, okay, let's, do a little bit of vector analysis. If you do an X transpose Y, now what is X transpose? X is n by 2, right? Okay, so X transpose is a 2 by n, right? Okay, so I mean, it's like a 2 by n, and then what is Y? Y is n by 1, correct? If you recall. So this is nothing but a 2 by 1 column vector. And what is Y transpose X? Y transpose X, once again, Y transpose X will be 1 by n, correct? Okay, and X is n by 2. Okay, so this means it is a 1 by 2 column vector. So what you see here, it's like a clear connection that X transpose Y is nothing but the transpose of Y transpose X. Okay, and we use that, I mean, while we simplify this expression. Okay, all right. Okay. Now, assuming that this is out of the way, what we can do is then take on this differentiation. Now we go back to minimizing the square of the error term, which is now I think I can safely write this as Y transpose Y minus 2B transpose X transpose Y plus B transpose X transpose X B. Okay, so this is it is a little bit simplified. I mean, I'm just trying to simplify this so that the differentiation process is easier. Okay, now what we are doing is we are differentiating with respect to the parameter B, right? And Y transpose Y is constant with respect to that. So therefore, when we take the partial derivative, this goes to 0. I mean, this will vanish, right? And then we have two terms which we have to take care, because both of these terms, involve the parameter B. The first term is easy. I mean, when you take the derivative of that, you are doing it by taking the partial derivative with respect to the B transpose, right? So this is really easy, because this guy will give us minus 2x transpose Y. No problem. Okay, the second term is a little bit complicated. The second term has B transpose on the left and B on the right. Okay, so it's sort of, B transpose B is norm of B square, correct? Okay, so I mean, you are taking the derivative with respect to B. However, we will leverage a simple rule that you perhaps recall when we studied vector calculus, which is if you have an expression in this form, then the derivative of that is nothing but, in this case your C is nothing but X transpose X. Is easy to see that, right? Okay, I mean, this guy is nothing but this X transpose X. It's easy to see that, right? Okay, all right. And so we can directly use this result to simplify this guy. Okay, so So what will we have then? I mean, if this is C plus C transpose, so C is X transpose X. So what would be C transpose? The C transpose will also be X transpose X, right? Okay. All right. So you have an X transpose X and an X transpose X times B. So basically what you will have is 2 X transpose X B. Good. Now remember, we are minimizing, right? We are minimizing with respect to the error. So the error has to be minimized, and if the error is minimum, then the parameters are estimated. You expect the parameters to be estimated as best as possible. So the error minimization condition is that this guy, so in other words, this guy is 0. So that implies that this guy is 0 as well. Okay. Now if that's the case, what I have here is that X transpose Y is nothing but X transpose XB. Remember, my goal is to estimate the B's. So what is B then? B is nothing but X transpose X inverse X transpose Y. All right. So what we see is that you solve the regression problem. Okay, the finding good fit to your data is actually equivalent to finding the maximum likelihood of with respect to the parameter. Okay, so finding what this means is finding a good fit. Bingo. Okay, this is great. All right, so the calculation does take some time, but then this gives us the platform to ask the next question. So what is MLE? A connection to any other. So this forms the foundation of the next topic of discussion. So I hope this is all right, and we can just move on. Okay, and we can give a more visual interpretation of maximum likelihood estimation and what it is about. All right. Okay, so let's do that. Okay, so now I mean the idea is, let's take an example. And this is like we're doing an exercise of a bunch of nursery kids. Okay, so there is a common wisdom that given that the age group, right? I mean, probably the likelihood of observing weights in a particular basket, right? And then there would be outliers, right? I mean, there would be outliers in the sense some kids are, some kids weigh more, some kids weigh a little bit more, and some kids weigh a little bit really, less, and all that, right? So the idea is, can we find a distribution that fits the data, okay, in a maximum likely way? So this is the question. Can we find a distribution? All right. Given what kind of distribution your data sort of follows, I mean, it could be exponential, it could be Gaussian, it could be binomial, it could be anything, right? I mean, but we know the form. As long as we know the form of the distribution, we are okay. All right. So in this particular case, we assume that the weights are normally distributed. Okay, so something like this. So what we observe is, a bunch of data is localized somewhere. Okay, and then what we also observe that there are some data over here. Okay, and there are some data over here. In a normal density function, there is a mean, and then most of the data is captured within 3 standard deviations around the mean, right? Okay, so I mean, and that's about 95%. Okay, all right. So 5% of the data is lies along the tail. Okay, so it is along the tail in this direction. So what will happen is, let's say this is normal. Okay, let's say this is normal, as most of the weights are captured around here, and this is low and this is high. Okay, all right. I mean, you could have a few nursery kids which weigh higher than the normal ones, and you could have a few nursery kids which weigh lower than the normal ones, right? I mean, and there could be more than one. There could be 5% of, I mean, if you sample 3,000 data points, is actually not a very low number. So you cannot really say that, okay, these are outliers and we ignore those and blah blah blah. Okay, all right. So typically what happens is, what we see is most of the measurements that we take are close to the mean. Okay, all right, and are therefore, I mean, since it's normal, it's following the normal density function, it's symmetrical about the mean as well. Okay, now once we sort of settle on the shape of the data, so this is basically the shape of the data, right? The next question that we ask is, how do we localize this? Okay, all right. So because there could be multiple locations of the mean, right? I mean, where do we settle as far as the mean is concerned? So the question is, I mean, if I have a bunch of Gaussians, right? I mean, you have, let's say we have, captured the most of the guys around here, most of the guys around here, right? Okay, but then you can have different types of Gaussians, right? I mean, you can have Gaussians with an elongated tails, right? Gaussian to the left, Gaussian to the right, and blah blah blah. So you can have something like this, right? You can also have something like this. Okay, now the question is, why do I want a bunch of other Gaussians? Because, I mean, I would want to know, because there are some data points over here, right? Okay, and there are also some data points over here. So what we try to do is, it's kind of moving a bunch of Gaussians from the left to the right. Okay, all right, and see which shape captures most of my data correctly. Okay, so as you can see, this guy as well as this guy, they do not really capture the data much, because, I mean, they only capture a fraction of the data. So from a representational point of view, I am probably better off not using this or using this. Now this guy, this particular normal density function and this particular normal density function, they do have some mean and some variance, right? So as this. So the question is, which one do I choose? Okay, so what should be the likely mean and what should be the likely standard deviation, so that I can describe the data well. Okay, all right. As we can see, in both of these cases, the probability that we observe most of the measurements is very, very low. Okay, all right. So with this in mind, the question that we ask is, there is this likelihood of observing the data versus the location of the center of the distribution. Okay, all right. So we want to find the likelihood of that location. So this is like, this question is equivalent to the likelihood. Okay, all right.